Chapter 3 is where the fun begins. We're going to look into actual elements, their chemistry, and how everything on the periodic fits together. But we had to cover the electrons and the quantum numbers from Chapter 2 in order to appreciate how important these electrons are and what they do and what their significance is. Okay? So, periodic properties of the element. And what we have here is an airplane, and an airplane uses aluminum as a metal for its construction purposes. We choose it because it has low density and it is strong, and that is entirely because of its electronic and nuclear makeup. And that's what we're going to look into in more detail. Alright, so here is a very simple shell model of an atom. And so what it represents, and we know some of this already, we have a nucleus in the center, right, with some sort of positive charge plus whatever. I'm not going to count them now. I think it's argon. Anyway, there's a nucleus in the center, and then you have electrons in different quantum levels, right? So if this was n equal to 1, we know that the number of orbitals that can be held is n squared. So n1 has one orbital, so which can hold up to 2 electrons. And so that's what we see here. We see 2 electrons on the first quantum level. They go closest to the atom. We also know that they are the lowest in energy. And that makes sense because in order to orbit on this shell, they don't have to go as fast as some of them on the second quantum level. So here is n equal to 2, and so n squared in this case is 2 for n equal 1. Sorry, 2 times 2, which is 4. So we have 4 orbitals and 8 electrons, and that's exactly what we see here. 1, 2, 3, 4, 5, 6, 7, 8. But it's a simple shell model, so what we don't see is the s and the p orbitals. So we know that some of these electrons are in p orbitals and some of these are in s orbitals. You go to the next level, n equal 3. We have 3 squared is 9, or times 2 is 18 electrons, and so we see 18 here. But now we also have d orbitals. But anyway, so we have these 18 electrons on the third quantum level, and they are in higher energy because they're further away from the nucleus, and they have to travel at a faster speed, so they have higher kinetic energy. So all that makes sense. It's a pretty simple model, and it fits right in with the quantum numbers that we had, at least partially, right? So n principal quantum number energy fits in here. What we don't see is m sub l and any of those things. But so we're going to look into it in more detail. This here, it describes exactly the problem I addressed earlier. We have electrons in an s orbital here, right? So this is n equal to 1, and then l equals 0. And then we go to the second quantum level, and so I'm going to get away from the n and the l and m sub l, just simply refer to them as like s or p orbitals. We know that some of these are in s orbitals and some of these are in p orbitals, right? Because we just don't have room to we cannot have more than 2 electrons in an s orbital, and we cannot have more than 2 electrons, so that's the nucleus, of course, here in the center, right? There's your positive charge, so you can have up to 2 electrons here. And so this happens to be the model for helium. Alright, so we're going to look at electrons, electronic configurations of elements, and this was done in chapter 1, atom, where I brought up the periodic table and the s blocks and the groups and all this. So it is important for you to remember that the periodic table is essentially has blocks. Okay, so we have the s block and the p block, and this really fits in over here, right? Because it has 2 electrons, right? So here's n equal to 1. So the first period has 1 orbital, an s orbital, and so the second electron goes into that 1s orbital. But we put it over here because it fills up that quantum level, and you get a noble gas here, helium, which has two protons, and so then we have the d block and the f block. Just remember that. I'll bring it back later it's going to help you with electronic configurations. Okay, let's back up a little bit and review how the periodic table came about. This is just a summary slide. I already mentioned that atomic theory goes all the way back to the hypothesis by Greek philosophers Leucippus and Democritus, who in 1440 dismissed what Aristotle said, matter is infinitely divisible, into, well, no, there's got to be a limit to it, and they based that on a hunch, looking at grains of sand that had individual components. So they said matter is made up of atoms, and they were right. But the sad part is that for 2,100 years, between 1440 BC and 1660, nothing happened. No thinking, no scientific discovery. And that's because mainly in Europe, religion took over, and they thought that atoms is blasphemy, that, so we were in the Dark Ages. Religion controlled everything. There was no scientific discovery. But there was a priest, philosopher, scientist, a thinker by the name of Pierre Gassendi, who simply made the statement that atoms are created by God, and that was good enough for the religious leaders to allow science and the pursuit of knowledge. And it wasn't, and so then in the 18th and 19th centuries, it took about a couple hundred years for Mendeleev to figure out, put it all together and put it into a periodic table. But it was Antoine Lavoisier who, for example, burned like mercury oxide and was able to collect mercury and decompose it into mercury and then oxygen gas. And so they would burn, and as I told you guys in a previous chapter, this is how they discovered all the elements, by burning and collecting and weighing and trying other different chemicals to it and collecting data. It took about a couple hundred years before Mendeleev put it all together and connected the dots. And he wasn't the only one, but he was the first one to put it into a periodic table. So this is Dmitry Mendeleev's first periodic table. It's different than what we have today. So we have here the second period here, right? So instead of left to right, these are up and down: lithium, beryllium, group 1, 2, 3, 4, 5, 6, 7. And what we're not having here is of course a noble gas. They weren't discovered until like 1870 or so. And so then we have the third period here, and then the fourth starts. There's something missing. You have the transition metals in here. So this is the third period, and so the D's are in here, and then it picks up. And so he noticed, he was the first one to notice gaps. So there should be a couple of elements that are here. This is gallium and germanium that are missing. They're harder to find because they're more rare. People hadn't discovered them yet, but he predicted that, and so he noticed these gaps, and he was actually able to predict their atomic mass, their density, and their ratio of how they would react, right? So, and this really here is very important, right? So he predicted that all of the group 3 metals would form compounds in let's single out the chlorides, in a 1:3 ratio. So this element that was missing here, he predicted that it would make XCl3, which was later then confirmed, just like aluminum would. Aluminum makes AlCl3. And so therefore, and then gallium would, and indium, the one below it, also makes InCl3. And sorry, that's of course, yeah, gallium, right? And then we have the one over, which is carbon, silicon, germanium, and tin, and so the germanium was missing as well, and it makes a 1:4 ratio chlorides. And so this is called a periodic trend, although it's more of a group trend, right? Because it's within the same group, but it's a trend on the periodic table, so we refer to it as a periodic trend. And so it's remarkable how close, how he predicted the density here, reactivity, atomic mass, and melting point for both of those elements very closely. And so he deserves a lot of credit from the scientific community. So this, as I said, there are periodic trends that we will discuss right after we look into electronic configuration. So here's that group where we had gallium missing. And so within that group, we have trends here, right? We have more and more electrons, meaning we're going to increase the size. So the atomic radius increases within a group, and that's true for every group. That's a periodic trend. There's an increase in atomic radius as you go down within a group. That's called a periodic trend. We also have a density increase as we go down, right? From boron to aluminum to gallium and indium here, right? So this is what we use in that airplane that I had up earlier, 2.7 grams per. It's light, not light, but it's not very dense, which makes the airplane less less dense and easier to fly. Overall lighter than, because the volume to mass to volume ratio, right? So remember that density is mass over volume, right? So that's a trend. Density increases as you go down a period, and you can actually explain that with what we know already now. All right. Okay, so it's a mass over volume increase. So as we go down, your mass increases, right? So that makes sense. But what about your volume? If that mass to volume ratio stays, right? I mean, your volume also increases in theory, right? So you have more and more electrons, and at least at first thought, okay? But here's what happens, right? If you think back at that first picture of the shell model that I had, right? You had a nucleus in the center, and then you had electrons, right? And so then the next shell had more electrons. So what's happening here is, as we go down from boron to aluminum to gallium to indium, we have more and more of these electron shells. But we are adding these electrons on the same quantum level. By the same token, we are increasing the nucleus in the center. So what happens is that pull has more and more of an effect the more electrons you add on a single shell here, right? So this actually gets pulled down. So the volume kind of decreases. I mean, it still increases overall, but relatively it decreases. So that makes the density even larger, since you're dividing by a smaller number. But we'll come back to effective nuclear charge and to density. For now, just understand that there are periodic trends. Now we're going to shift our gears a little bit and look at electronic configurations. And so we are going to be most interested in the outer electrons, those that are on the outermost shell, right? The highest quantum level, that are not embedded. Those are the ones that are going to do the chemistry. They are going to either be removed or share. The lower lyings do not so. But and so if you remember the m sub s quantum number, it was said that we either have a plus or a plus a half or minus a half. What we do here is we put little hooks, right? We put them, this is an orbital diagram. We already know, for example, that boron has 4 electrons total, and that the first quantum number is n equal to 1, and it has an s orbital, right? So we have a 1s orbital, and you can actually just write it as a line art. And glitched on me, just a little line instead of having that circle. You put a 1s over it, the first electron goes in. We have put it with hook up, and then the second electron you put it hook down, indicating plus 1/2 and minus 1/2. Then the first energy level is full. We go to n equal 2. N equal 2 can have either L equals 0, which is an s orbital, or L equal to 1, which is a p orbital. And then we have 3 different orientations. So we have the px, the py, and the pz. But we don't distinguish here. We just write 2p. Let's say 2p, and we write 3 lines. And there's just the 4th electron goes in it, so we just have 1 hook here. So that's called an orbital diagram. And so this is how it's indicated. The plus 1/2 and minus 1/2 is simply indicated by hook up and hook down. Okay, and so even simpler than boron, let's looking at helium. We have an electronic configuration. We know helium has 2 electrons, and so the very first orbital is a 1s orbital. And so we can just say, okay, we can have a little superscript 2. And say there are 2 electrons in there, whereas hydrogen would be 1s1. And that's how it is for thallium, which is atomic number 81, right? The very first orbital is going to be the 1s1, and it's going to be full, right? So that's 81 electrons for thallium, and then we still have 79 to go. So we keep going. So, but how do we know? How do we keep going? And we do this by using the Aufbau principle, which is a German word, means essentially building up. We just fill one orbital at a time. And if you remember the quantum numbers, you can actually figure out what they are, right? So 1s2, 1s, 2s, 2p, and then 3s, and then 3p, and then we also have 3ds, and so, but how do we know, and how many, and what is the capacity of each? Well, we know that, and I'll just say this real quick, S is going to have a capacity of 2, P is going to have a capacity of 6, D is going to have a capacity of 10, and F is 14, which is reflected on the periodic table. Okay? So, what you can do, and I learned this in high school, but you just write the numbers down from bottom up, 1, 2, 3, 4, 5, 6, 7, and then you do this and you draw these lines through it. That tells you how it fills. The 1s fills first, then the 2s, then the 2p, then the 3s, then the 3p, 4s, and after the 4s is the 3d. This is how you remember, because that's that discrepancy by drawing this little chart up and down, right? So that's one way to do it, or you memorize it. This is just another way this is written. But the easiest way to do it is I'm going to bring you back to the blocks, right? We have these blocks. Remember, S block, P block, D block. And we also understand that the periodic table is arranged by energy level or quantum number, right? So the first period is 1, 2, 3, right? We have these layers here. The first period can hold up to 2, right? 3, 4, 5, 6, 7. Hang on. I can do this. 7, right? And then maybe some of you remember that here is actually the 3 and 4 and 5, and that the 4F, which is what this is, the 4F, is inserted here after 57, right? After lanthanum, we go down here. So if you remember that, and let's say you have to do the electronic configuration of gallium, all you have to do is you look at the periodic table and you go from the atomic number 1, you just follow it. And so what we have here is the first atomic number is 1. It's in period number 1, so that's n equal 1. It's in the s block, so that's an s. That's the 1s. So the second one also goes into the 1s. Then we come over here. This is the s block, so we have a 2s, right? These 2 electrons go in a 2s. We come over to atomic number 5. We're in the p block. So now we're filling the 2p, okay? 2p. Then we run out of at 10 of p. So we come down here. This is the 3. This is, again, we're in the s block. So this is the 3s. Nothing here. We're still in the third period. We now have a p block. We're still in the third, so this is the 3p. We run out at 18. Go to number 19. 19 is now in the fourth period, so this is going to be 4. It's in the s block, so it's a 4s. But then we are inserting a d block here, right? So scandium 21 is in the d block. It's the 3d, so that we have to remember. 3d, that's going to be 10, like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 3d is full. So now gallium is in the p block here, right? This is the p block. And there's 1 there, and this is the fourth period, so this is the 4p, and there's a single electron there. So now then we just go maximum capacity, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p1. If it's germanium, 4p2. Arsenic, 4p3, right? And so on and so forth. I love saying that. I should give you bonus points if you catch when I say that again. Yeah, let's do that. If you tell me when I say that from here on out, so on and so forth. You give me the lecture, you tell me the time, and I'll give you a bonus point. All right, moving on. Okay, so there's this weird thing where I told you that the 3D goes in the fourth period. Well, which really isn't the fourth period, it's the third period. But why is it not up higher? Okay, here's sort of why it is, right? Remember orbital diagrams and their relative energies, but we just looked at n equal 1, 2, 3, 4. So the higher we got, the closer they got in distance here, right? And so this is the reason why these electrons fill in the 1s. The 1s is the lowest in energy. It gets filled first. It's closest to the nucleus. We put 2 electrons in, bam, full, right? Then we go to the next orbital. Just what we've been doing by looking at the periodic table. So 2s, 2p, 3s, 3p. And then the next one is the 4s, right? So we put 2 electrons in there. And then we have that weird drop. We have that scandium, which is 21, and it's a 3D. An empty 3D orbital is higher in energy than a 4s orbital. But what happens as you fill these orbitals, their energy changes slightly. And so the minute you populate putting an electron in the 3D orbital, what happens is it drops in energy. And this will become important at some point. For right now, it's not all that important, but if you are a chemistry major and you will benefit from understanding that the energy lowers here. And the same thing again happens with the 4F drops all the way down here, and the 4D drops one. Once you put an electron in there, they actually change in energy, right? And that's where they are the 3D and not the 4D. All right, so if you don't quite get that, just remember the 3D starts here, so which makes that 4D, 5D, and then the 4F after barium 56, we fill the 4F. So it's barium, it's 6S, and then 4F, and then 5D. And so you can know this by simply looking at the periodic table without having to memorize this here, right? So here's what I was talking about, like the 3S, then the 3P, and after the 6S you have the 4F, and then the 5D, which is what I was just showing you here. 6S, 4F, and then 5D. And if you just remember the blocks, right? D, S, P, and F, and paying attention to the lines and remembering these exceptions here, you can do this by just looking at a periodic table. All right, what do you say we've practiced a few of these, and I am only going to ask you to follow the Aufbau scheme. Okay, so what we just did, follow the periodic table. So if I ask you to do this for nickel, you would go, okay, so nickel is going to be, I'm going to write it over here, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d8, which is sort of what's down here, except it has nickel and then it has argon, and so, well, it is focusing on the valence electrons, or the electrons that are important for bonding, which are the highest ones in energy here. And that's why we all the way up to here, 1s2, 2s2, 2p6, 3s2, 3p6, that is the electronic configuration of argon. Oh, big mistake here. That needs to be a little r. No, I was going to put Arkansas. I think that's probably what it is. A capital R. It's Arkansas. That's why I did that. Terrible. I've only lived here 16 years. All right, so we can just then say, okay, so this is the electronic configuration of argon plus 4s2 3d10. Now, in reality, what happens, as I told you, once you populate the 3d and the 4s, they switch in energy. Okay? And this becomes important later on when we make ionic compounds. Ionic compounds are metals that lose electrons. And so something like nickel will lose 2 electrons. And it's going to lose the ones that are highest in energy. So it's going to be the s electrons that are going to go poof. All right. But for now, we are just gonna stick with Aufbau, right? We're gonna not worry about ground state. You know, if you got some available brain cells, shove that in there, or maybe just store it there for later. It'll help you. Okay, so again, let's get rid of this ground state here and just look at Aufbau. So then something like arsenic, which if you have a periodic table, bring it. Pause the video, get a periodic table, look at it. Find arsenic, it's atomic number 33. All right, so arsenic, if you backtrack and look, what's the closest noble gas going backwards? It's going to be argon, right? So argon has 18. It is as shown, so 1s2, blah, 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 all the way to 3p6. We can just abbreviate it. And I'll ask you that. Write the complete electronic configuration or write the abbreviated. Or an orbital diagram. You ought to be able to do an orbital diagram as well. All right? So then argon, once argon is filled, the 4s2 is filled, then the 3d, and then the 4p. And so the 3d is full, the 4s is full, and the 3p has 3 electrons in it. Okay, it's atomic number 33. If I ask you to draw an orbital diagram, you want to draw the 4s2 and just remember it. Just represent it with a single line, and then the 3d you would put 5 orbitals, 2, 3, 4, 5, and then the 4p would have 1, 2, 3, and then you put your electrons in, up and then down. And so for the 3d, they're all full, but what you do is you fill each electron with a single electron. See, they spread out. That's Hund's rule. Hund's rule says electrons will spread out before they pair up, but once you've put out 5, you pair them up. So, and then 10. And again, you have 3 more to give. You want to spread them out. That's important. You spread them out. They don't want to crowd each other. If there's an available p orbital, if there's a px, py, and pz, one electron will go into each orbital, and they spread out. They don't get into each other's way. They will only pair up if they have to. And pairing energy costs a little bit, okay? I might want to pause. I'm going to pause, and we're going to come back, and we're going to practice doing the electronic configuration of all of these atoms, the abbreviated, with noble gas core, without it, and orbital diagrams. So see you in a minute.